Hello, everyone. My name is Renalyn Paras, and just like you, I am a full-time university student studying to have a great paying career that I also enjoy. And at the same time, I am working 2 jobs so I can pay my bills, make a living, and pay my tuition. So, going home and from home to school, and then from school to work, and after work I go back home to do more schoolwork. It is my daily basis, or my daily life. Therefore, I drive and I walk a lot on a daily basis. So I decided to do my stretch presentation based on commuting, but more specifically on my own daily life. I am basing my stretch presentation on how I get to these many places more affordably and efficiently. So, let's talk about the one most important thing in the world: money. Well, more specifically, how to spend money more affordably. So let's start by making an LP on what I spend on a daily basis on how I get to places, or how I commute. Alright, so let's start by introducing some variables. My first variable is x1, which represents my the time I spent per hour parking in campus. So, parking in campus is $3 per hour, mostly everywhere. But where I park is the education building, because all my classes other than this class is actually in the education building, because other than this class, I only have education classes. The awesome thing about the education building is that there's a $15 daily maximum. Therefore, I wrote the constraint x1 lesser or equal to 5, because $15 divided by 3 equals 5, which is the max hours that I will pay in parking at the education lot. So beyond 5, it's free, so it doesn't matter. And I wrote 3x1 to represent my $3 per hour. My second variable is x2, which represents the time I spend parking per hour in downtown. So in downtown, if you park in the street, the maximum is 3 hours, and beyond that is a $50 ticket. So, pardon me, by the way, I am quite really sick right now. So, I wrote the constraint x2 lesser or greater than 3, because beyond that, I'll be paying $51 for a ticket for parking for 3 hours or more, and I do not want that. And I wrote 2x2 on my objective value to represent the $2 per hour. My next variable is x3, which represents the liter I use while I'm driving. So right now, the gas price is $1.40 per liter. It fluctuates between gas stations, but the one I use is Co-op, and at Co-op it's $1.40 per liter. This variable may change depending on the day, depending if it's later in the evening or where we are in Saskatchewan. But right now, I chose this because that is what it is for co-op everywhere in Saskatoon. And this 2.22 without a variable is stagnant because that is my registration for my car. My registration per month is actually 68.89, but I divided it by 31, which represents the days of the month, which equals to 2.2. And it cannot be a linear program if the variables are negative numbers. So this constraint represents that all my variables will be a non-negative number. Further, time cannot be negative, and also a liter of gas can't be negative either. All right, now we've finished talking about my daily spending on how I get to places. Now let's talk about efficiency. And when I talk about efficiency, I'm talking about how I get to certain places as fast as I can. Well, right now, my main place I go to is school. Not school. Main place I go to is work. So, I'll show you a map from Google Maps of around where I live. I live around here, but I won't tell you the exact address for privacy reasons. And I work around here. I actually work at Lululemon. Alright, so there's actually 3 different kind of pathways I can choose to get to work. I can go take the 22nd route and get to work that way, or take a right as soon as hit 22nd and go through 20th Street and then take a left and get to work. Or I can take the Circle Drive route right around here and then get to work. So I drew a graph that represents those kind of 3 options of ways to get to work. And I also inputted vertices that are like checkpoints on different pathways I can take. So I have vertices S, which is here, and to T, which is where I want to be. Now, we need to know the cost of these edges in order to find the shortest way, to calculate the shortest way to get to my destination. So I also used Google Maps once again to the rescue, which was very tedious and time consuming, but I placed pins here and a pin there to determine how the distance between this and here in terms of kilometers. And I did that for each vertices and each edges. It took a while, but let's skip to the next slide, which shows the cost of each edges by distance in terms of kilometers. As you can see here, all of these are in kilometers. So in the short path algorithm, we may just choose the shortest way to get there, like the shortest distance to, and say that is the most optimal way to get to work. But as you can tell that each road, not as you can tell, as you know, each road has its own maximum per hour. Like for instance, this road is 50, and as soon as you get to 22nd, this is 60, and then after this turns to 50, all the way to work. This is the same thing. This road is 50. So this whole thing is 50 kilometers per hour. But if we take the other route, this is 50 kilometers per hour, and then it changes to 80 kilometers. Then it changes the max to 90 kilometers per hour. That's the max here. And then over here is 60. And over here is 80. And it goes back to 50. So I converted using just simple math such as cross multiplying to find the minutes rather than kilometers for my cost of my edges. So I made sure these are equal, and then I cross multiplied, and I used 0.6, which is this distance between S and B versus S and B. And I found out that 6 kilometers, if you drive 50 kilometers per hour, is 0.72 minutes it takes to go from S vertice to B. And I used Desmos. So it was to pinpoint all of these time more efficiently, just like the main topic of this presentation. And I also needed to calculate it to convert seconds to minutes. And to simply do that, there's 60 seconds in 1 minute, so it's 1 out of 60, which is around 0.16 per minute. 1 second equals 0.16 per minute, and 3 seconds equals 3 over 60, or 1 over 20 per minute, which is also 0.05 per minute. This will be important for next time. All right, now you can see either the cost being kilometers. Now it's based on time, which is what we need to find the shortest way to get to work. But in a regular road, there are stoplights and stop signs. And I drive this road a lot, so I know which ones have a stop sign and which one has a stoplight. We have to take that in consideration to calculate the amount of time to get to my destination. And as you can see, there are many stoplights, but some of them don't really matter, because for here, even though this is a red light on our lane, we don't have to follow that because we can just turn right. Unless there's, of course, traffic coming, so you have to stop and yield for them. But similar to here, this pathway won't have to add extra seconds because you're just turning right, but this pathway will have to add extra seconds because if this was a stoplight, of course you have to stop. So, factors we need to consider. The average stop time is 1 second less or equal to 3 seconds. But let's assume that we are a good driver here, so 3 seconds will be the stop time, which is 3 out of 60, or 0.05 per minute. And I found an article that shows that in Regina, the average minimum green time is 7 seconds, and the average maximum green time is 90 seconds. And the average amber time is 3 seconds. So the time for the red time would be the green time plus the amber time, because it will be red all the way until it turns green. But for this presentation, let's just assume that all of the green lights last 20 seconds and all the amber lights last 3 seconds. Thus, the red stop lights last 23 seconds, or 0.4 minutes. Let's also assume that we are having a really bad luck day, and all the stoplights turn red. And also, it's also not a bad thing to think that all the lights turn red, because if we were trying to time how many minutes till we have to leave our home, then it's great to take in consideration the highest amount of time to get there. Also, you have to take into consideration the car acceleration time to get to the needed speed. So I did some research, and for my Honda Civic 2001, the average time to get to a certain speed is from 0 to 60 miles per hour, or in Canada, where it's 0 to 96 kilometers per hour, is 6.3 seconds, which is around 0.05 minutes or 0.11 minutes. Alright, so I changed all the needed edges by adding the needed considerations. Like for here, obviously we're gonna be accelerating, so I added the 0.11 minutes to the 1.32 minutes to get to this vertice. Same thing here. And for this very, very long edge, since there's 2 stoplights, and you would have to accelerate to the needed speed 3 times, I calculated plus 2, 0.05, which is 3 seconds for the 2 stoplights, and plus 3, 0.11, which is the 3 accelerations that would happen in this edge. And I didn't add for the ones that are just red lights, because you just keep going. And you see over here, I actually just used T here, and this needs to be R, because S is only used for my my initial location. And same thing here. I did the same thing. I added the amount of time you have to wait till it turns green, and also the acceleration time. All right. Now, let's use the short path algorithm to find the shortest path to get to work. Iteration 1. Let's make some SD cuts. So the very first SD cut will be this, and the shortest one is 0.83. Therefore, my U will be SB, and my new YS will be 0.83. And for the second one, since we can still fit a cut here, because 1.43 is still bigger than 0.83, I make a cut right here. I mean, not right there. My apologies. you can't make a cut there because it's an arc. So I make a cut for SB, which is our U, and there are three things here. There's 0.48, 0.72, and 1.43 minus 183. And that is 0.6. But even though we minus that, 0.48 is still the smallest, so therefore it becomes the new arc and becomes the new ST cut. Now for the next one, iteration 3. We're cutting off SBA, so let's make a cut right here. Oh, and this one turns into 0.48. So this in here, that the cap, what it actually has right now is 0.72 minus 0.48, which you can see over here. No, not there. Here. 0.72 minus 0.48. And it's between this edge or this edge. But this, since 0.24 is smaller than 1.56, this one becomes an arc. Alright. I hope you get the idea, because it's the same thing the whole time. And it's also demonstrated in this graph right here. It might be a little messy because it's quite big, but you can see all the ST cuts. Alright, after all these cuts, we can see the arcs that we collected through doing the short path algorithm are these ones, but the ones that we did not use are, we did not use KO, we did not use EF, we did not use IJ, we did not use WM, OP, or QP. This should be QP. QP. And the total equals to 11.91, which is also the same total as the width assigned throughout the shortest path algorithm. These are all the widths assigned through the shortest path algorithm, and I added them all up, and it's the exact same thing as the total equal of the edges or the arcs that we use to get to our destination. That means since we found an ST's path whose length is equal to the total width of a set of feasible ST cuts with, this path is the shortest. But although it's the shortest, does that mean it's the most affordable? No, it does not. Because since we're parking downtown, let's say I work 3 to 8. I would only have to pay $3 an hour. Because after 6 o'clock, parking is free. And the distance of the shortest path we chose, which is, I can show you right here, which is this, which represents in the graph that I made for my SD cuts. That one right here. We can see once we add all this distance together, it equals to 6.82, but that is in kilometers, and our cost is in liters. And I found out that my Honda Civic is the cost in a city is 7.4 liters. So I did more cross the multiplication, and I found out that 6.82 kilometers equals 0.50 liters. And if I added that to my LP right here, it will cost me 0.71 for 1 day, but $9 for parking, which is 9.71. But if we took this road instead and park in M, which has free parking, and walk all the way here, it takes way longer. It takes double the time to get there, but once we calculate it, it's actually way cheaper since we don't have to pay for parking. It's only 0, and the distance we use for the car is only 6.37, and using cross multiplication, we found out that 0.47 is the liters we use to get to for a destination of 6.37 kilometers. So my daily consumption for parking far away and then walking versus parking close and paying is actually 14.69 times more than if I were to park in downtown or not pay for parking and just walk. So as you can see here, there are many different ways to solve this problem, and there is many different circumstances. For instance, if I'm late, I would want to get to work as fast as I can, so I would probably take this path rather than this path, because I do not want to be late for work, or else I'll get fired. But if I want to save money, I would take this path. The only thing is, it's the longest way to get to work, or not the shortest. All right, thank you for taking a peek on my presentation about affordability and efficiency on commuting, and taking this and using a short path algorithm, but in a way bigger scale, to find a way to get to my destination in the shortest amount of time. Thank you so much.